So we're going to talk for the next 5 minutes about stressful floodplain design and shear stresses. Um, shear stress is the weight of water, 62.4 pounds per cubic feet in U.S. units, times the depth of flow in water or the hydraulic radius times a slope. Shear forces are really important because vegetation, floodplain, um, and everything around it kind of is a response of what the shear forces will be applied on a surface at any given time. So if it's wind-borne systems like a coulee in Canada, it might be something where we're looking at aerolean sediments, but if we turn water onto it, then we're going to have a change where water is going to be the force, and we're going to have a shear and force based on the weight of water. So one of the things that we do in looking at floodplain design, we look at a channel restoration design, which could be based on the 100-year channel, the 50-year channel, the bankful channel. We say design for a range of discharges, but then we also look at the floodplain characteristics and how do we design a floodplain for the vegetation that's available to recolonate or for the vegetation that we replanted. So one of the ways that we go out to the field is we look at rack lines after storms, and we look for deformation in the floodplain. So in the slide that you're looking at, if you have it, you'll see places where you start to see deformation in a cut floodplain. And the idea is we look at how high deposition was or how high the discharge was associated with that shear force, and then we can calculate what the shear stress was when there was deformation occurring. So if we do this on enough sites in a regional location, then we can get a new reference for each parameter related to floodplain resistance coefficients. And we can say, hey, we think that there's going to be this vegetation that can establish in this location, and in this general region with the rainfall and with the vegetation potential, we think that you may be able to withstand 1.2 pounds per square foot. So then we can reconfigure floodplains and flood terraces for that distribution of shear forces. One of the things that we noticed in gulches in the West is that a 100-year discharge, the shear forces at the 100-year discharge, the 200-year discharge, and the 500-year discharges don't significantly change because the distribution of the average boundary shear stress spreads out and it gets wider as it gets higher. And this is one of these things where it kind of helps us understand how gullies have formed in time and why we can take such a steep drop in places where we have sandy soils. Usually it's because we have floodplains that have been able to be readjusted to this average boundary shear stress. So we talk about average boundary shear stress and critical shear stress on floodplains, and it's really important for us to look at the conditions in the field, opposed to just saying, hey, well, we think we're going to be able to get 2 pounds per square foot for resistance on a floodplain. In the past, the Army Corps of Engineers has published out of Vicksburg, Mississippi, Craig Fischnick and others published information related to what the critical shear stress for deformation of floodplains was. And in those areas of high rainfall and vegetation, they've come up with numbers like 2 to 2.5 pounds per square foot. In the semi-arid West, we have places where we really can't get more than 1.2 pounds per square foot. There's other places. This is a place where we have a very, on the one side we have good groundwater infiltration because we have a pond. So in those places, we're able to see 1.8 pounds per square foot in the West. There's other places that we can't even get to 1.2 pounds per square foot. And so the goal is that we want to be able to get reference conditions for floodplain resistance to deformation from stable reference reaches, things that are able to be achieved within the lifespan of a restoration project. So here's a project in Colorado on a gulch. It has a resistance of 2.4 pounds per square foot based on rack lines and deformation on the floodplain, but it also has a willow community that takes over 100 years to grow. So it's always kind of a balance on what can we achieve in the time frame that we have for restoration. So we have many ways to kind of mitigate for excess shear stress. You know, treatment and seeding and strawing with riparian plants, treatment of coir or matting. These are all things we've been doing for years. Treatment of log sills, silt cutoffs, silt trenches, and then also vegetated riprap and other treatments. So there's a lot of different ways we can deal with excess shear, but I think it's important that we're looking at floodplain design, that we think about that floodplain shear, and we design appropriately for that. So we're moving towards ideas of 4-stage channel designs, multiple channel designs. So we designed for a bankful channel, we designed for a floodplain, we designed for an inner berm channel, we designed for a flood terrace. And these are all important when we're having frequent flooding, to make sure that we're designing to a shear force that's appropriate for the vegetation that could be established in the expected time frame that these surfaces will be accessed. So that's kind of the way that I look at it. So for example, 100-year discharge, well, I'm probably going to be okay with using a vegetation type that's going to take closer to 100 years to establish, because, well, I'm only going to see a discharge there on average in 100 years. Now, I know that a 100-year discharge can occur, multiple times in a year, but if I'm trying to manage risk, that's one thing I'd look at and say, okay, well, here I have a vegetation that can establish in 50 or 25 years. That's probably a good resistance to design for the 100-year discharge. Whereas in the flood terrace, in this green box, we probably don't want to design for that because it's going to occur a lot more frequently. So those are kind of my thoughts today on shear stress design. Does anybody have questions related to looking at reference shear stresses from field indicators?
Dave, what are the units on the table on the bottom? Obviously, the first one's, I'm assuming, the flow. And
yeah, I'm sorry about that. It's just a background on there. They all have units up on top, but it's just blacked out. So we have a discharge, and then we have the cross-sectional area, the depth. So we have the mean depth, cross-sectional area, velocity, slope, and shear forces. And then the shear forces are down here at the end that are covered up. And I will resend that out. I'll just change the background so the units are on there on the slide. I have some verbiage over here that came up that was blacked out when I put it on here too. So I'll resend that out to the group.
Thanks. It's good reference information, Dave, for people, just their rules of thumb. I mean, that's, after you've been doing it for so long, you've got great rules of thumb, but some of us who haven't been doing it that long don't have those rules of thumb. So I really appreciate you finding ways to pass those on to us.
Yeah, and the real key here is that we want to be able to establish these in different regions. Like if somebody says, hey, I have 14 inches of rainfall a year, we can probably get you about the right shear stress. And we're looking at trying to put this together in ways that say, okay, this is where different rainfalls, this is where you should have for critical shear stress for different channels. But that's going to be a ways down the road. But pretty much everybody could go out and look at a stream and identify deformation, the floodplain, and a rack line and say, hey, this is what the shear stress was for this deformation. So that's kind of the thoughts that we'd have. So.